Hi, and welcome everyone to the third Unicorn seminar in our topical blog series on space-based tests with optomechanics. As always, please mute yourself in Zoom and turn your video off to save bandwidth. And if you have any questions during the talk, put them into the Zoom or YouTube chat, and we will forward them to the speaker. Before I introduce the chair of today's session, I would like to advertise next week's program. So next week, we are hosting a panel discussion with different academic and industrial stakeholders involved in the UK's roadmap on space exploration, and how in particular space-based tests with optomechanics fit into this broader context. So today we have the great honor to have Lisa Werner chair this session. Lisa has worked in different areas of quantum physics, such as molecular interference, frequency stabilization, and atom condensation. She's currently at the German Aerospace Center, where she leads the efforts to prepare the Bose-Einstein condensate and cold atom laboratory for deployment on the International Space Station. Thank you very much for sharing today, Lisa, and the floor is yours.
Thank you very much for that kind introduction. It is my honor to now chair the session, and the first speaker of the session is going to be Jasmine Decidu, who is a researcher in quantum information theory. He did his PhD in quantum sensing and estimation theory and is now in Strathclyde. Jasminder, the floor is yours.
Thank you very much, Lisa. Going ahead. Okay, you can see the slides?
Yes.
Awesome. So yeah, thank you very much for the invite. It's a great pleasure to be involved. So today, in keeping with the theme of what we can do in space, I'll give a bit of a discussion in terms of what we're trying to do using satellite-based quantum communications. So I'll start with addressing the question of why do we want to distribute quantum states? So from that will stem a range of different applications before we hone in on to introducing satellite quantum communications. We'll then discuss current efforts, so some of the missions that have either been proposed or are already underway, demonstrating key milestones in realizing a networked infrastructure. And then I'll summarize with a quick conclusion. So why do we want to distribute quantum states? So the idea here really is networked quantum technologies. That's dedicated quantum technologies working together and yielding greater capabilities. And so from that, there are kind of 4 distinct applications that come to mind. A lot of these do have crosstalks, and some of that will be revealed in the coming slides. But the first one is distributed sensing, astronomy and imaging, testing fundamental experiments, and the final one that most of this talk will be concerned with is quantum communications. So in distributed sensing, some of the things that you are able to then have is optical clocks, make precise estimates of fundamental experiments that include space-time parameters. It's useful for metrology, navigation. In astronomy and imaging, basically you have access to longer baseline interferometry, and that's going to be useful for example, gravitational wave astronomy. And there's a lot of experiments that you can do for fundamental physics with access to space. And part of that is testing alternative theories that fall outside the remit of the current standard model, exploring relativistic effects on QKD, which is basically things that are not accessible with purely terrestrial networks, and also just exploring how entanglement evolves through close to massive objects. And on the side of quantum communications, which in some ways is one of the most earliest kind of quantum technologies, is the realization of this quantum internet, something that's going to impart a similar revolutionary impact as what we currently know as our normal everyday internet. But there are a lot of technologies that need to be still developed to realize this networked infrastructure, and part of that is like quantum memories, quantum repeaters. You need to be able to distribute entanglement across the network, and part of that, as we will see in the coming slides, is realizing satellite links. So just to have a look at some of those applications in a bit more detail. I'm a theorist, so I like to have a few equations on the slide. So in distributed sensing, the idea really is that you can make precise estimates where the precision is at least better than what you could achieve classically. There is a fundamental limit to how well you can estimate parameters, and that's governed by this inequality, which is called the quantum Cramer-Rao bound. And the idea here really is that you want to determine what this matrix is, this matrix I, the quantum Fisher information matrix. And there are various ways you can determine this. It all depends on the geometry of your probe state that you choose. But one such example is this so-called Sld Formalism. The key point is that it depends entirely on your probe state and its dynamics with respect to the parameters. And so the idea here is that you need to carefully select the probe state such that it's sensitive to slight changes in your parameters. And this will become clear to address what the optimal probe state is in a distributed fashion. Yeah, the RLD formalism is another method of calculating this quantum Fisher information term, and it's important for multiple parameters. Now, ideally, when you measure multiple parameters for different sensors, it's not so meaningful to have this matrix inequality. So we usually cast it as a scalar quantity, which is defined as the trace of the weighted mean square error. So let's cast this in terms of what this means in terms of an actual practical setting. So here, basically, we have a networked approach where we decompose, say, a vector of parameters across 5 different sensors, which could be entangled, and hence the red dashed lines. And this setting it's useful for a lot of distributed sensing applications. So that could be phase sensing, estimating properties of multidimensional fields, which more intuitively extends to this idea of having space segments. You can also use it for more abstract things such as calibrating CV-QKD networks. And the idea here is it helps you address what the optimal probe state is. So specifically, if you're estimating single parameters where each of these subsets is just a single parameter, so not multiple, then it doesn't really make sense to make global measurements or have global states. And in fact, it can be detrimental to have these entangled states. So if you have multiple parameters, then it really depends on the commutativity of the different parameters, and that can determine whether you should have entangled probe states. So for astronomy and imaging, the idea here is that if we network multiple telescopes, it gives access to larger baselines, which is useful again for fundamental physics, precise measurement of time differences, and improved resolutions. And that's going to be useful for a lot of interferometric applications, such as this black hole imaging that we saw. This is the Messier 87 that was observed by the Event Horizon Telescope, which is a large telescope array, which effectively gives access to an Earth-sized telescope. So these are all radio telescopes, and there's an emerging field of quantum astronomy, which works on optical telescopes, which really haven't seen much in the way of progress up till now, primarily because it's more expensive to realize, so it's harder to get this cluster that attains this larger baseline, but also because astronomical objects really emit powerful radio waves, not so much in terms of optical signals, and whatever optical signal they do emit, they're usually degraded in terms of transmission through the atmosphere. So it's quite an exciting time in terms of having optical telescopes. So for the final application that we consider is the global quantum communications. And the question is, why is this important? So it comes back to the networked infrastructure and the quantum internet that we want to realize. And this itself has a lot of applications for distributed sensing, secure quantum communications, and distributed quantum computing. So on the right, we have a kind of a depiction of different stages to a global quantum internet, where each stage represents an increased functionality of the network at the expense of greater technological difficulty. So for example, the final stage is where you really need to start being able to perform fault tolerance operations, so you'll have large overheads. So this really is going to be long term. So yeah, this requires a network infrastructure to realize all these quantum technologies. So the current barrier that we have to global networking is lossy channels. So it imposes a direct limit to the transmission range. One way we can overcome that is through the use of these quantum repeaters, which essentially these are devices that break the transmission line into shorter segments where the loss is small. So as you can see, basically the entangled photons through a series of teleportation into quantum memories using Bell state measurements, you can effectively increase the length of the fiber link. Generally, you get these kind of multi-hop quantum networks where basically each node has this mesh topology for a quantum network. And basically quantum communications can be realized between any two nodes, even if they're not directly linked with a quantum channel. So all the nodes here are making Bell state measurements independently. And this is, it has the advantage that it can reduce the hop-to-hop transmission delay. So one thing to bear in mind is that these quantum repeaters, they're not ideal. So they're still being practically improved, but also quantum memories. It's another technological factor that is important for networking, and these platforms use either atoms or ions, but they need special interfaces because quantum memories don't really operate at telecommunication wavelengths, so they need converting before they integrate into optical links. And we also need to improve the storage time and the efficiency of coupling. And so this kind of links to improvements in optomechanics, and really improvements in that are required to be able to extend and use this architecture. But quantum repeater also have their own limitations in that each of the links have the same exponential loss. So, for example, you will need a quantum repeater station every 20 kilometers, which in principle is possible, but it's in certain geographical places it wouldn't really be an option. So this is where the use of satellite comes in. It can reduce the number of ground repeater stations that are required, but also the intersatellite communication link has considerably less noise with respect to ground links. Using satellites has its own not so much disadvantage, challenges, which is that there is loss in the uplink downlink channels between an optical ground station and a satellite, and also there are these limited transmission times. And so these are some of the challenges that we're currently working on in satellite-based quantum communications. Even still, if you compare the link efficiency for different distances, you can see that satellite link is a lot less noisy. So this really will pay dividends in terms of realizing a networked infrastructure. So for satellites, there are basically many different types of links. This we're illustrating an uplink, a downlink, a double downlink for entangled photon pair distribution, and you can get these general intersatellite links. And of the things that we are working on is establishing links between satellites and OGS, reliable connections, optimal network configuration, and these inter-satellite links. And then the idea is basically you will have arbitrary networks, both terrestrial and space segments, that will be able to coordinate quantum communications between any two nodes. So in terms of what the progress is on that side, QuES, which is the Chinese mission using a low Earth orbit satellite called MISIUS, is making huge leaps in terms of demonstrating key milestones. So, for example, downlink exchange of cryptographic keys, teleportation of single photon qubits, and entanglement distribution survival. And recently, they've also integrated a hybrid quantum network using space links, which has resulted in a total communication distance of 4,600 kilometers. So this approach really is making headway. It's not so much just a theoretical kind of concoction. So QuES is an example of a huge traditional satellite. And there is the rise of these nanosat efforts, or CubeSats, and there's a demonstration of the anatomy of a CubeSat on the right-hand side. And the first such, or rather one of the missions, is CQCOM, which was a consortium growing out of a UK-Singapore effort. It's a 6U CubeSat mission, so it will be 6 of these 1U CubeSats stacked. And it was going to use a downlink configuration with the Matera Laser Ranging Observatory in Italy. So this mission inspired a range of others, such as the SpookySat, which is a Singaporean effort based on a 3U CubeSat. And one of the aims it had was of demonstrating uplink and downlink and key sharing between different optical ground stations. So just to illustrate the different size, we have this traditional MISIUS satellite, which is quite big, expensive to develop, and then we have the CubeSats, which are really small, and it has the advantage to that it's really easy to it has a fast development time, cheaper, so it's a great tool to be able to test different space experiments. There are a lot of other commercial efforts, such as Quartz, Arcit, Quark, and ROX. And here is like a timeline of the key missions. I won't really go into much of the detail, but the takeaway from this is that satellite-based quantum key distribution and more generally communications will be possible. And one of the things that we are beginning to see is that the number of missions using CubeSats is increasing. So it's going to indicate its prevalence in this approach. And yeah, the whole idea of using a network is basically still something that we're trying to demonstrate with CubeSats. So a lot of this detail is in the archive paper on the bottom, which is Advances in Space Quantum Communication. So a lot of the details I'm having to skim over for now, but do have a look at that if you want to have a look at more details. So just as a last few slides, I think it's worth to say that optomechanics plays a key role in hybrid quantum networks, and so it enables quantum communications between quantum systems. And specifically, the importance is the interface between photons and quantum repeaters. Okay, just finishing. And so what we can use is some of the takeaway messages from space quantum communications and use that as an enabler for future optomechanical experiments. And just to summarize, that CubeSats it provides an ideal platform for this because it has a rapid development time. It's cost-effective approach to increase coverage as opposed to these traditional like the MISIUS satellite, and quantum transmission of quantum sources has actually been demonstrated as possible. Some of the key enabling technologies that must be adapted is the sources and detectors, optomechanical design of CubeSats, and adaptive optics, so to improve the link quality. Yeah, quantum memories, they play a central importance role in networking. So just as a quick summary, satellite-assisted quantum communications are necessary for global networking, and they'll be necessary for space-based experiments. They are receiving a surge of interest, and they have started to realize important milestones, and so it wouldn't be of any surprise if they become the main platform to test future experiments. Okay, thank you very much.
Thank you very much, Jasminder. We do have time for one quick question, which came in from Sophia. She asks, she was wondering if satellite-based observatories or telescopes would solve the problem with repeaters and infrastructure.
It will reduce the demand on repeaters, but you will still need quantum repeaters to have terrestrial networks. It's more a matter of using satellites to link different networks.
And Stefan also has his hand raised. So Stefan, what is your question?
Yes, one short question. You stressed pretty much that it seems to be going in the direction of CubeSats. If I look at a operational rollout of a QKD system, let's say the framework of EuroQCI or something like this, do you think that this is the way it's going to go? I would be interested on this.
So there is definitely more of an emphasis on CubeSats in terms of it's cheaper. So in terms of accessibility, it wouldn't be a surprise if it does go down that route, but yeah.
I mean, cheap is always the question. How do you define it, right? I mean, at the end, what your customer wants is cost per qubit, basically. And yeah, it's going to be interesting. I think Saga, for example, the ESA study is going toward the totally opposite direction now. So 1 meter telescope in space on a geostationary satellite. Yeah, so we'll see. It's going to be interesting.
It will be. Yeah.
Thank you very much. Thank you very much, Jasminder, for the great talk.
Thank you.
And it is my pleasure to introduce our next speaker, which is Christian Vogt. He's currently at ZARM with Mr. Lemmitzal, and he has worked on cooling neutral atoms in dipole traps and wants to use in microgravity and wants to use his experience now and apply that to nanoparticles. And he's going to talk about cooled nanoparticles in a drop tower today. Thank you very much.
Great, thank you. Yeah, I think you can see my slides, if that is okay. Okay.
Yes, I can see your slides.
Okay, that's cool. Yeah, so what we want to do, I'm going to start with the atoms because we've done that already, and then I'm going to hand over to the nanoparticles, which we are planning. So what we want to do is we want to use these atoms to measure very tiny forces, and therefore we apply atom interferometry. And I'm not going to go into the detail here because I just don't have the time for that. But it starts so that you have a cloud of cold or cloud of atoms, actually, basically. And then you can use laser gratings, which you see here, to put these atoms in a superposition with different momenta so they move apart from each other. And then if you use another intelligent beam split or another intelligent grating, optical grating, yeah, you can reverse the momenta in here and then recombine these two. And then depending on the phase these atoms have accumulated over the different paths, they're gonna end up with different numbers in these two output ports of the interferometer. And what's important now that the sensitivity of this actually scales with the time they are in free evolution in here where nothing happens squared. So we want to do this time as large as possible. So we're fighting two things here. The one of them is gravity, because we're having atoms. They're going to fall down. We can't use them anymore, which is, for example, here in a vacuum chamber. And the other one is that there's the temperature, because the atoms will just fly apart and we can't use them anymore. So the solutions are obvious. We want microgravity, which is what we're doing. And we want to have them as cold as possible, so ultra cold atoms. And that is then around nanokelvin or something is where we end up. So the road to space is a bit difficult, and everyone knows that it's quite expensive to go there, and it's not easily accessible. And if you send your experiment over there, up there, you can't change anything anymore, basically. And you have to worry about the power and the size of the experiment and the weight, which you do not have to think of in the laboratory, at least not much. And 2 weeks ago, we heard from the LISA Pathfinder experiment that there was kind of a gamble and whether they would have success or not, because they just sent it from the lab to space and they were very successful. That was great. But you could also use this step in between where you can use ground-based microgravity facilities like the drop tower that we have in Bremen, or the other famous one now, parabolic flights, which you can see in Bordeaux, for example. So this is, the video starts, at least for me, so it's kind of bumpy, sorry, the Zoom connection is not too good. So we have a tower, this is our drop tower, where you can drop your experiment for 110 meters of height, which is giving you approximately 5 seconds of microgravity time, and you can also use a catapult starting from the bottom, which is giving you then like 9 seconds of microgravity time. This entire tower has a vacuum tube inside, and that has to be evacuated for every single drop. So that means we are limited to 3 drops per day, but having a very good microgravity quality. While we're hanging in the tower and it's evacuated, we're having a cooling water connection, and some power supply. And in the next pictures, you see how this is disconnected, and then you can actually see the drop from the bottom of the capsule, as seen here. This takes a while. And if we go, then if we're making it to the bottom of the tower, the capsule or the experiment is decelerated with these little styrofoam balls that you can see flying around in a second. And this, we're hitting these with approximately 120 kilometers per hour. And so it's decelerated with approximately 40 G. So there are several experiments for ultra-cold atoms and weightlessness. And I've listed them here, and you can see that basically there's a difference in having them trapped magnetically or optically. And these are on the left-hand side, the ground base, which is in the drop tower then as well, like the project I'm working on, we're in the drop tower as well. We do already see these cold atoms in magnetic traps in space. So Stefan will tell you a lot about this in a second, or in 15 minutes. And there's also a future mission, which is where Lisa is working on, the BCAL mission, which is like combining the best of these two worlds. So the question is, here's a void for the dipole traps for space today. Why is this the case? Well, the main reason might probably be that we still need very high power lasers. We are using 20 watts or 10 watts of optical power, and these are very large and they are heavy and they need a lot of power. Of course, electrical power as well. And so it's not possible yet to bring them to space. So this is also this is all about bringing optomechanics to space. You have to think of something like this as well, if there are problems. This is our experimental setup. And on the left-hand side, you can see a typical structure that we need for the drop tower. You can see 4 aluminum stringers, and then there are several platforms in between that you can arrange as you want, more or less. And the entire experiment has to work autonomously when it drops. So you can see that we have a bunch of batteries with us, so we need no connection to the outside world whatsoever. And then, there's the vacuum chamber, of course, because we have to operate these in high vacuum. You see our dipole trapping laser and some electronics that we need. This is basically then the vacuum chamber that you see, and the way we're trapping our particles, or we're trapping the atoms, is by having a single focused laser beam that is then recycled and sent again into the chamber. So they're crossing at the center of our vacuum chamber. And so we're doing several cooling steps, which is basically we're starting with laser cooling, and I'm not going to talk about. So the difference between the optical traps and the magnetic traps is important for us here. And that is the way we're doing this evaporative cooling. And evaporative cooling is, so to say, one of the last steps to get really cold temperatures. And you can imagine that you have a Boltzmann distribution of your atoms with a certain atom number with a certain velocity. So this is the initial distribution. We're gonna get rid of the high energetic tail of this distribution. So we're left with a distribution out of equilibrium. And due to rethermalization, which is that the atoms collide with each other, they're gonna form the same distribution again, but then at a lower velocity. So we reduce the temperature. And the way this is done for optical traps, you can see here the potential of our optical trap for different laser powers. And we just actually reduce the laser power, and therefore the traps become shallower and the hot atoms can escape. And you can see this already is tilted, so this is in the direction of gravity. And this is important because actually, yeah, it's about how to get to space with the nanoparticles. Actually, I'm going to show you a bit of things you have to think of. So it's more the problems and the solution I'm going to give you here. And one problem we had is the beam displacement. So as you can see here, so these are the two beams actually as they're crossing. This is the potential they're forming. And it's obvious that you want to have these stabilized. So you want these to be very stable and always crossing at the same point to have reliable information and repeatably results. So we observed that this is kind of difficult. We saw that these beams do not cross anymore when we went to the drop tower, and then again it went worse when we released from the top of the tower. So in the transition from the 1G hanging there and 0G and microgravity free falling, there was also a shift between these lasers. So you can see here some kind of a side view of our trap. And you can see that this is the unstabilized laser. So this is the added information from these lines, the vertical lines. And you can see that there's not really a cross anymore. And if we stabilize the laser, then we get it back again. So the great thing about this solution is that it was an off-the-shelf solution, which is if you go to space, to microgravity, that's already a problem. If you go into space, it's even worse. You can always think about they have to build your own things at home because you just won't find the fitting solution for space. And then another problem that we're still hanging on right now, but it's nice to it's a nice impression of what can happen in microgravity, is that when you reduce the power further, then at a certain point this tilting comes into play, and the lower the trap is, the more of these. The lower the trap is actually in gravity, but it does not in microgravity. So there's kind of a difference, and it gets worse with the lower power you're using. So we can easily achieve on ground a BEC with 100 milliwatts of power left. It's not a problem, as it's done in several labs around the globe. But if we go into microgravity, we do not see a BEC. I forgot to mention a BEC. BEC is just the state that occurs when the atoms are extremely cold and kind of dense. So they form a BEC, a Bose-Einstein condensate, and this is what we actually want to reach. So we do not see this transition anymore in microgravity. So the problem now is that you could of course just decrease the power further, but the problem is that we have a photodiode that we need for the active intensity stabilization of the laser, which is important to get stable conditions, and that is not able to resolve in the dynamic range from 20 watts, where we're starting, to 10 milliwatts to the end of the evaporation ramp. So what we did, we built in an LCD liquid crystal display in front of the photodiode, and we could get better results with that. But then we're running actually into the numerical resolution, so the signal we're given to the AOM, where we're steering the intensity of the laser. So this is just to give you a mindset of what you have to think of, what you have to consider if you plan something to bring into microgravity, that you just have to rethink everything. And if you need changes afterwards, that is very hard to get because you have a very compact setup everywhere. So changes are really hard to get through. But with this, I want to leave the cold atoms, and I want to talk about nanoparticles, levitated optomechanics. And we want to bring them to microgravity, to our drop tower as well. The project is called NICE, which is a German word for then nanoparticles in weightlessness. And we're thinking about measuring gravitational forces. We want to do something like inertial navigation. We want to just test it out, what's possible. And of course, we're interested in what we heard last week from Rainer Kaltenbeck, for example, the quantum mechanical behavior of large masses. So this is the experimental setup that I have in my lab now. And this is pretty strongly based on what you can see in Hendrik Ulbricht's lab, because yeah, we're sticking to what he did before, basically. So you have a laser that is amplified. Actually, the AOM and the EDFA are interchanged by now. So the laser is amplified, then sent through an AOM that you need for reducing the power of the beam. And then you're sending it to a vacuum chamber where there's a parabolic mirror in there. And the first thing I have to say about this laser breadboard has a length of 30 centimeters. So it's very appropriate for space mission. It is uncomparable to what we are using with the cold atoms. So there's not a limitation on size, weight, or power for this. You can easily send this to space. Of course, there's a question of stability and things like this. And actually, the only experimental result I have from this yet is that we were able to trap a particle that you can see on the right-hand side on the bottom. And yeah, that was trapped with 140 milliwatts. So the laser powers are definitely different from what we need from the cold atoms. So the easiest way that we could think of, and it's been done before in this Hebestreit paper, for example, is that you have a particle that oscillates with a low amplitude in the potential, then you switch off the potential, have a certain force acting on the particle, switch on the potential again, and then see actually where it moves, or in this case, how large the amplitude is now. So we thought that it might be possible to have a gravitational test mass next to the chamber that is approximately 10 centimeters away and has approximately 50 kilograms. Well, these numbers are not carved in stone, but this is something we could think of, and that should be measurable. But there comes another problem in here. If we're calculating these with nanoparticles, for example, in the ground state, as it can be found in the Aspermeyer group, you're left with about 10 microkelvin, which is a lot hotter, of course, than the cold atoms. And that means you have velocities of 10 micrometers per second. And 10 micrometers are about the size of the trap. So that means if you're having it flying freely, the particle for 1 second, it's gone. You can't reach it anymore. So the first step would be to get the particle either colder, which could be done by preparating it in a less stiff trap, in a shallower trap, so the ground state energy reduces. Or you could also just reduce the power of the trap to have it slightly trapped, not have it freely flying, but have it slightly trapped. And these are the things we want to do. These are basically then our targets, our first targets in microgravity. And which is what is very important here is now we show the feasibility of these techniques. And that is, of course, then also the foundation or the support for any space mission that is planned for nanoparticles, for levitate nanoparticles. So we can do our job here and support these missions in that way. And of course, then we want to try to get very low velocities as far as possible. But with this, it's already quite the end. We're also thinking about how to get these ideas of matter wave interferometry, or to just see the wave character of these large particles. And then there is it was proposed in this Bateman paper, for example. I think most of you are familiar with this, that you can do also interferometry with nanoparticles. Basically, this is on ground. So we do not think that this is appropriate for the drop tower in this way, because you just have one particle per run. And if you think about that, we just have 3 experiments per day at a maximum rate, that you need stable conditions for all of these things for over several days or weeks to get an interferometry pattern. And this seems to be really, it seems to be impossible for us. So our experiment then that we thought of might be easier to approach is that we have the particle cooled and then have a grating, shining a laser grating in there and have the particle reflected on this. So therefore we can measure that in a single particle, that we do not need an interferometry pattern anymore, that we can see that the particle moves the other way. It must have been quantum. And that is based on, move faster. This is, we're using this for Bragg reflection, and I have some kind of a simulation, which is not running. Now it does. So it should look something like this, because a classical particle would just move over these potential barriers because they are attractive. So you're gaining, and conservative, so you're gaining as much energy for every well that you're leaving it. So whenever a particle is reflected, you can see from a single particle that this has to be developed by quantum mechanics. And so there are certain numbers, and the question is how fast you approach the grating and how deep it is. And you can see that there are several areas where you will see Bragg reflection, and this is what we're hoping to see. The problem with this is that these are some hopefully realistic numbers. So for smaller particles, the reflection itself takes less time. So this should be done in the drop tower, but as soon as we get into larger masses, you see that at least the reflection process itself takes 2 seconds, which is too long and out of reach. So we're thinking about now how to use standing waves for this. Yeah, and this is what we're actually looking for. So my conclusion is that space is technically challenging if you want to go there, of course. And if you want to go to microgravity, you always have to think every single step that works in your lab. It might not do the same in microgravity. But I think the most important message is I see no technical reason why it should be impossible to send levitated optomechanics to space. Either on the sun, in a rocket, or on a satellite should be possible. Yeah, I'm going to finish. Thank you for your attention.
Thank you very much, Christian, for that very nice talk. And again, Sophia has a question for you. And she asks, would it be possible to trap 2 nanoparticles adjacent to each other and then drop them to see how they interact?
Sure, it would be possible. It's the question on, well, yes. We're thinking about this as well. What the next step in the ultra cold atoms is that we use dynamically shaped potentials. This is the next step. We need this for what we're doing, and other people are looking into this as well. So it naturally comes to our ideas to have double well potentials or something like this. The question is then maybe on how to load these, and yeah, there might be some difficulties that we have to overcome, but definitely we're thinking about trapping several ones of these.
Yeah. And also Peter asks whether the 355 nanometers that you chose for the laser wavelength would lead to ionization of the particles. Is this something that you have considered, or is this not an issue?
No, I did not consider this. I just not randomly chose this, but there was a wavelength that I thought of would be handleable.
Okay.
Shorter than this is just unimportant. But let me just finish this with the laser powers are extremely low. I was kind of shocked with these 5 milliwatts. And if we're going to this, there's okay, these ERs. It's not good in here, but we're talking about numbers from 1 to 10. And if you're using 5 milliwatts for this, we're at 300,000. So they are very low laser powers. I do not think about that ionization would be a problem.
Thank you very much. In the interest of time, I'll come swiftly to Stefan. Stefan has worked with Ernst Rasel on Marius and on cold atom experiments for space. And he's currently with Airbus, and he's here today to give us a talk on cold atom interferometry in space.
Yes. Can you hear me?
Yes, I can.
Can you see my screen, which I will put in
Yes.
Presentation mode. Okay, perfect. So yeah, thank you very much for having me today. So my name is Stefan Seidel. I'm with Airbus Defence and Space in Ottobrunn, close to Munich. I'm going to give you a very short overview over atom interferometry and Bose-Einstein condensates, some pathfinders, and an outlook. First of all, just a very short look at what we are doing at Airbus. So we are Europe's largest prime contractor for optical instruments, for space missions in total, actually. And this is, I'm working here in the optical instruments division, and we have a very broad range of optical instruments we're developing, ranging from cameras, hyper and multispectral imaging, spectrometers and LiDAR systems, and then something that is now more and more coming into focus is what we call quantum metrology. So yeah, instruments based on quantum effects, let's say. And today I'm going to talk about one of these possible instruments, which is atom interferometry. And first of all, what is atom interferometry? We have seen this before, but just to give you a very short summary, the idea is you reverse the roles of light and matter when you compare it to a normal or to a laser interferometer. So you can see a laser interferometer, your beam is coming in, you have a beam splitter, you have two mirrors, you have another beam splitter and two detectors. And now I reverse the role by replacing the optical wave with a matter wave, and by replacing the mirrors with standing light gratings, basically, that act as your beam splitters and mirrors. And here, what is important actually is that the phase difference between the output ports here is directly dependent on the force acting on the atoms. So you can use this to measure any forces that might act on your atoms, and that the sensitivity scales with the interrogation time, with the square of the interrogation time, actually. So interrogation time is basically the time between your light pulses. This very simplified symmetric case. So how does the measurement cycle look? We've seen this before in Christian's talk very briefly, at least the end of it. I'm going to go through it quickly also in the interest of time. So first of all, we do laser trapping and cooling, which I'm not going to explain you. Basically, it's the idea that you use inhomogeneous optical and magnetic fields to trap your atoms based on their atomic structure. Then you transfer them into a magnetic trap, and this we have seen in the previous talk, and you do evaporative cooling. Then you can release them. And now we're in this picture on ground, so they will fall down and you do your interferometry scheme. And you do your detection and start over. During this time, and we've seen this before, your atoms will expand, and they will fall a certain distance, and this will limit your measurement time. So we have to get rid of both of these effects. And first of all, how to increase your measurement time, and this is to go to BC, or to at least something that is very BC-like. And here you can see in a comparison and the expansion rate between something comparably warm at 200 microkelvins above absolute zero, something a bit colder at 2 microkelvin, and then a BC, which is at 50 nanokelvin. Yeah, it's all pretty cold, but the difference is still big, especially if you look at this. I hope you can see it, that after something in the order of seconds or of hundreds milliseconds, these two cases have basically disappeared into space, or into your vacuum system, while with the BC you can still see after seconds. So basically, the BC, the use of a BC, enables you to do go to longer evolution times. So you have lower systematics because your system is small, your atomic cloud is smaller at the end. You can have higher beam splitter efficiencies, and you have higher detection sensitivities, densities. The other problem is to increasing the measurement time is that you still have gravity hampering you. So the idea is basically you go from a lab experiment, like you can see on the left-hand side here, with maybe free fall distance of 20 centimeters. Then you go into a fountain system, 10 meters, let's say, but that might still not be enough. You can calculate 10 meters. I think it's something in the order of 2 seconds. And so you might want to go to something called something like a co-falling laboratory, so satellite. And basically here the idea is, I mean, your satellite is still falling in gravity. It's just at the same time rotating around Earth, and the forces are compensating each other. So you're basically creating a co-moving laboratory that moves with your atoms, and you have also some advantages over building such a fountain, that your atoms relatively to your experiment don't move a lot. So you have to control your environment on a much smaller volume. And due to some, at least if you measure something like gravity, you have some benefits that allows you to measure gravity, and that's basically that you're modulating most of your signals, if it's a gravity-related signal, with your orbital period. Okay. There's a challenge then. We have to get this, okay, not a typical lab experiment, the first BEC experiment ever built at MIT, into this. And you can see already that there's a problem. Actually, this is Vogt for those who are interested. And the issue here is that, okay, you need to reduce mass, you need to reduce volume, you need to reduce your power consumption, you have to ruggedize your experiment against the environment, and you have to do it autonomously. And also because it's going to be quite costly to send your PhD students to space, you need to have a reliable operation. It's not going to be possible to adjust your lasers in space. So this is something that needs pathfinders, and one of the first pathfinders, or the first pathfinder that brought the BC into space, and actually we've seen all the other pathfinders beforehand in Christian's talk, which is quite nice. So we basically can just have a look at the rocket mission here. Marius 1 was the goal to bring BC into space. And to basically to gap the bridge between lab and space, and it was designed. So I was working on this when I was still at university. It was designed to withstand launch and re-entry conditions, which are listed here. They're comparable to large satellite missions, not totally identical, but at least in the same order of magnitude. I think the biggest difference is the operation in vacuum. That's going to be quite challenging for future missions if we go into the operational scheme. For this, a scientific payload was built, and this payload is seen here in this red cylinder. The cylinder was actually hermetically sealed, so it was under ambient pressure, diameter of about 0.5 meter and 2.8 meters tall. It contains 5 subsystems: a vacuum system, a laser system, a electronic system with a computer, where the 5th subsystem, which is the software, is included in the power control system. Total mass about 315 kilograms and an average power consumption of 300 watts. And here the atomic species of rubidium-87 was chosen. The experiment was launched in 2017, so about 4 years ago, and achieved about 6 minutes of microgravity. And here microgravity I define as being above 100 kilometers, and the effective acceleration is then below 10 to minus 5 g. And during this time, during the whole flight, about 110 experiments were conducted. Of those, 81 in microgravity. And if you want to look at a picture of what has been done there, we can briefly go through it. So after launch, down here at S-Range in the north of Sweden, first there were done some quite nice experiments while the boosters were still burning, while the rocket was burning. Then then the first creation of a BEC in space, at least a human-made BEC in space. We don't know what other people did. Then some experiments on the characterization of the BEC, some experiment on their magnetic state separation, then magnetic lensing, which is a technique to cool your atoms even further, and at the end, Mersenne-type atom interferometry. Then the system landed again in the snow, was there for 3 days and recovered later, and was still operating after some minor repairs on the water cooling system that was integrated in the system. Just a very for a look at the first BEC in space as a highlight from this experiment. So it was created about 100 seconds after liftoff. During that time, the instrument was at an altitude of 132 kilometers and traveling with a speed of 4.2 times the velocity of sound at ground, which actually doesn't make any difference, but still a nice number. And the atom was actually quite remarkable. So the BC had a size of 2 × 10⁵ atoms with a thermal background of 8 × 10⁵ atoms, which is quite nice because it's actually showing that at least magnetic evaporation is working quite nicely under microgravity conditions like this, which was was quite a nice result. So this for the first pathfinder. Then I think the other very important pathfinder is the Cold Atom Lab, which is a experiment built by JPL for NASA. It's a multi-user experiment facility on the ISS that you can see here. And on the ISS, they have built the instrument inside an express rack. And it contains basically very similar subsystems than Marius, just in a very different configuration, because the exterior conditions are very different. But at the end, you will have a laser system, you have your vacuum system, and inside your vacuum system, in this case, again, you have 2 chambers and then atom chips, which we also had in Marius. And here they showed some nice pictures in their publication of the astronauts installing the system, which is, maybe quite an advantage if you go to the ISS, that you can maybe exchange your systems also later by these high-trained astronauts. They had a very, very important achievement with CAL, which is the first creation of a BC in orbit. And I think this already shows one of the advantages of going to the ISS, and that is can do a lot of experimental cycles. It's basically like you have your experiment in space, your lab transferred to space, so you can basically just redo your experiment, optimize them in space, something we could not do with Marius, where we basically had to define our list of experiments beforehand, and actually the experiment was working autonomously. They have shown quite a nice example here of the phase transition between a thermal state on the left-hand side and a partly condensed BC. I think they said 26% in the BC. Yeah, looks a bit more, but maybe my eyes are seeing this wrong, but anyhow, so about 5 × 10⁴ atoms in the total ensemble. So if we take 26% of this as being condensed, it's about 1.5 × 10⁴ atoms. And they've done a lot of more experiments afterwards. And I think the nice part here is that they can use this facility to also have other scientists come and work with them and do some very fancy experiments that you wouldn't maybe get your funding for a dedicated mission. And this also now leads us to the outlook. As a first outlook, there's going to be 2 more sounding rocket missions. First one called Marius 2, the second one Marius 3. And here the idea is to include, in addition to rubidium, also potassium, an optical dipole trap, and microwave state preparations. And this enables the main goals, which is creation of BC mixtures in space and dual species atom interferometry. And then there's going to be a second multi-user facility build, which is called the Bose-Einstein Condensate and Cold Atom Laboratory, BCAL. It's a joint venture between DLR and NASA, basically to build a multi-user but also multi-purpose facility on board the ISS with significantly enhanced capabilities compared to CAL. Just to list a few of these possibilities, it's going to contain rubidium and potassium atoms, BC's atom interferometry, Feshbach fields, and I think also time-averaged optical potentials, so-called blue box. The system is going to be built by Germany, so by a German consortium led by LISA actually, and it's going to be launched and accommodated by the US. As a further outlook, what are future prospects from my point of view? I think there are quite a few scientific ideas that are really interesting. So equivalence principle tests, dark matter search, gravitation observation. We've already heard decoherence experiments, which are also very closely related. Then a field that's very interesting as well is to use these systems as sensor for gravitational Earth observation. maybe it will help us to address some of the very urgent topics of humanity, like climate change. And last but not least, I think we have very high shared technology foundation with atomic clocks. So there's going to be a lot of synergies with developing one and the other. Maybe just as a final remark, I don't have a slide on this actually, but yeah, as a possibility, basically, to demonstrate your systems, I would also like to advertise the Bartolomeo platform, which is going to be, or which is installed on the International Space Station. It actually allows you to bring a experiment to the International Space Station on the outside of it, comparably cheap. So if you want to have a free view on Earth or not, or on the stars or something like this, while still having some of the advantages of being on the ISS, this might be something very interesting for your demonstration. Okay, so yeah, most of the work I've presented here was actually funded by DLR Space Agency, and there's some papers to be read that you could read if you're interested in learning more about it.
Thank you very much. Thank you very much. Stefan, are there any questions? Okay, if this is not the case, what do you think is the biggest challenge for cold atoms in space in the future? Where would you say we would need to invest most?
For cold atoms, I think currently, I mean, the current status here is basically that we are an academic. I mean, the academic work is very what's the best word? Yeah, it's progressing extremely fast, but I think now what we have to do is basically go from, at least if we want to go applications like this, like Vogt or Grace-like missions, we have to do industrialization. I mean, this is what we are doing at Airbus, is to look at all systems in such a cold atom experiment and turn it into an instrument. Yeah, I think I would say it's addressing almost everything. The most mature part might be the laser system so far, at least if you look to France. And the most, and something that's always overlooked is for sure how electronics are built.
Absolutely, I agree with you there. Thank you very much. Oh, there's another question from Peter Barker asking you how much better the performance could be as opposed to Grace, or how much?
Yeah, it's a bit complicated. Okay, so you can't really specify this with a single number. Yeah, I think so depends also on the way, on how you realize such an instrument. So let's say if you take Grace and you replace, so Grace consists of 2 satellites like shown here, and each satellite, the satellites are, the distance between the satellites is measured with a microwave or laser link, let's say Grace follow-on, so with a laser link. And you have 2 accelerometers on each satellite to measure your non-gravitational accelerations. And if you replace these, or if you support these gravimeters on your satellites with a quantum gravimeter that is better in the low frequency range, you will also be better in your gravity recovery in the low frequency range. And so basically you could improve your static, recovery of the static gravitational field significantly. I don't want to give a wrong number here, but I would say, yeah, it's in the order of one order of magnitude, I would say, for low frequencies. But there are also very different ways to do this. I mean, you can also go in a Vogt-like configuration. Then the numbers are actually, so Vogt-like would be 1 satellite and 6-axis gravity gradiometer. And here you would have an advantage almost on the whole spectrum, so on the whole frequency range that you're observing.
Thank you. And I've got a final question from Thomas from Streba, and he's asking you about the most important lessons learned from Marius and Cal. What's your take on those?
So for Cal, I cannot really speak as much because I was not in the project. For Marius, I would say, yeah, what's my lesson learned from Marius? I think it's that this is, I mean, Marius was a tremendous amount of work, and but I think it was on the edge of what's possible in this context. So I think really, like what I've said before, industrialization, professionalization of the work is needed. Get engineers involved early because, yeah, they are, and actually now, so I would say differently. Now that I've worked in the industry for a while, I would say there's a lot to be learned from industry when it comes to techniques that we use every day for our classical optical instruments. A lot of the stuff you are facing when you build, for example, the stuff with to levitate your nanoparticles, as we've seen before in the talk, I think there can be learned from industry on how we build our optical systems, which is entirely different. We don't have anything we can adjust. Basically, there's techniques to build stuff so that it's adjusted. Yeah, it's a bit more complicated than this, but I think there's a lot to be learned also in this direction, which is it's not magic or anything. It's just clever engineering, which has been established for quite a while.
Thank you very much, Stefan. So I guess I'm giving back to Marcus. Is that the idea?
Yes, thank you very much, Lisa, for this fantastic sharing today. And also thank you, Jasminder, Christian, and Stefan for the 3 very nice talks today. Thanks to the audience for joining, and be sure to tune back in next week for our panel discussion on Wednesday, 2 p.m. British summer time. See you all. Bye.